wanted to write Stan again, but I still needed to use Stan. So this tool that I'm going to talk about is helping me fulfill the stream, but you cannot see it. So what is the matter? What do you think? Okay, pops up now. Magic. Right, so I have some, so it's called StanBlocks. It's actually completely misnamed. So it came about when I had some Julia backend implemented that mirrored basically Stan's blocks, right? That's why it was called StanBlocks. But now it has shifted to this blockless transpiler from some subset of Julia syntax into Stan. So but I never really got around to renaming it. Yeah, so there is some live transpiler because I can never get people to use Julia, no matter how much I extol its virtues, and nobody wants to hear about it anyways, right? At least not David, as far as I know. You have the slides on the right, and then also some, unfortunately, LLM-generated documentation in the middle, if you want to check this out. Right. So this is now StanBlocks syntax, right? So you have some Julia-style macro, which is called this add slick. Then you pass data, which is x and y. And then you have some relatively concise syntax, right, which allegedly mirrors Julia syntax, but it's actually very close to Stan, right? So because I wanted to make my life easy in transpiling this to Stan. So if you then ask for Stan code, it will give you the Stan code, right, with the obvious things being put into data, so the x and y parameters, which in this case you don't know from the slick model, but these are vectors. It will then figure out what has to be a parameter. It will insert the constraints for the sigma, for example, right? And then it will figure out what has to go to the models block, with what has to go into the generated quantities block. So in the end, StanBlocks is really like a front end for Stan, right? So it makes your life or my life easier when writing Stan models, and it's much more concise, and I think it's very powerful. I don't know whether anybody should be using this actually, except for me, because I know what works and what doesn't work, right? Documentation is either non-existent or written by agents, right? So which always get things wrong. But I think it's helpful to me. I don't know whether it will be helpful to anybody else, right? And in the end, so my slides are actually just this, right? So it's basically something that mimics Stan syntax, but with added quality of life improvements, which I don't know whether they are in the works or whether they are ever going to land to Stan. It's blocklessness, probably not, right? I know that people are working on closures and maps and everything, right? But what this basically allows you to do, right? So it does activity analysis to figure out where things have to go, right? Into which block. It allows you to specify submodels, so you have reusable modeling components. So you can have user-defined types, which, for example, allow you to handle ragged data easily, which allow you to handle named tuples instead of simple tuples where you always forget, was the one now X or was the one at the second field of the tuple Y, right? So I think names are much easier to remember than numbers. It allows the user to define higher order user-defined functions, so functions which take other functions as arguments, and it will basically figure out how to make Stan handle this, right? Because obviously Stan can't handle functions as arguments to other functions, except of course in certain cases. It supports closures, it supports keyword arguments, default arguments, all the kinds of things that you could wish for that are present in other more general languages such as Julia or Python are available or can be made available and potentially work or don't work. I mean, for the use cases that I use StanBlocks, things usually work, but of course there are many sharp edges, right? So that's also why I don't really recommend anybody use this, but maybe if people use it, the sharp edges will be discovered, right? So it does all kinds of things, right, basically. So in principle, I could stop here, but I think it makes sense to give you some more details, right? So the first question is maybe why would you even want to put like another stack in front of Stan, which is itself transpiled to C++, right, and which is then transpiled to machine code, right? I don't know whether anybody in their right minds would want to do this. And I mean, if I had the choice, I would be using Julia, right? So because I like Julia and I like the language, and as I said, I don't want to write Stan myself. And Julia it's a great language. I don't want to go into it. But there have been problems with Julia's integration with automatic differentiation, basically, right? And I think Julia and Stan basically they started from the same seed, so to say, right? But they diverged into different directions, right? So with Stan explicitly always having AD as one of its core concepts and always targeting probabilistic programming, while with Julia always targeting bare metal performance, but mostly only for the primal pass, right? So for non-AD based computation. And Julia's AD history is fraught basically with things being wrong or slow or both. Things have improved on the Julia side, so at some point I might discontinue StanBlocks and switch to Julia. I don't know. Stan, Stan is a good target to generate code for us because it's very explicit. It's very explicit about what it does, what is a parameter, what isn't, right? So it's also has a reputation of being reliable, right? And it generally is. So that's the quintessence, right? So Julia maximizes the freedom that you have to express your programs, while Stan makes this all very simple for the compiler, right? This is basically the same thing, right? So it's basically, Stan generally, it gives you good performance, not necessarily the best one that you could wish for, but in general, getting good performance is easy. Getting the best performance is maybe difficult or impossible, but in Julia, it's often the other way around, right? So getting very good performance takes a lot of effort, and if you simply put in very little effort, then you get very bad performance usually. Yeah, Stan is reliable. Stan has been stable for a while. You can always pinpoint, you can always fix some Stan version, right? And Stan code itself is a good review boundary, right? So if you have an agent generate the code, right? So then you still have something that you can check, or even if you have StanBlocks generate the code, you also have something that you can check either yourself or that you can have checked by agents. Yeah, and I hope, I don't know, I've checked out BRMS's generated Stan code. It's quite general and powerful, but I think it can be a little bit opaque, right? I don't know whether StanBlocks' generated Stan code is much better. I try, but it's, of course, not always easy, right? Right, so now, again, back to the what, right? So we had the why. So this is, again, the example from before. And as I said, so what's missing are the block declarations. What's missing are the explicit types, the explicit shapes of the parameters or the data. These are optional, but inferred if you don't provide them, right? So you could say that sigma has to be areal, or that sigma has to be bounded from below by 1 if you want it for some reason, 2 for some reason. The main caveat of StanBlocks is that it doesn't allow this top-level control flow, because and that's a choice that I made because I want to be able to do this activity analysis easily, right? And if I allow parameter-dependent control flow, that just makes life much more difficult for me. So that means there are no top-level for loops in the model block. There are no if-elses. There's no continue and no break, of course, because there are no loops, right? There are primitives to get around this. There are ways to generate batches of parameters. There are and in user-defined functions, you can do whatever you want. So use whatever control flow you want. But I disallow it in the model declarations surface, basically, right? And then basically, that's again the Stan code emitted from the first example, just a little bit more exhaustive, right? So now you see the data up top, and then StanBlocks actually also gives you ways to compute these common things that you want from your model, like the point-wise likelihood, or to generate predictions. Right, so as I said, so the compiler or the StanBlocks figures out the placement of all your parameters. It figures out the representation, so what are the Stan internal types and shapes, and what are the constraints, what are the function signatures that have to be generated to make this work in Stan, and so on. And it also then generates these likelihood statements and predictive quantities for ease of downstream processing. Right, and I think the main kicker here is maybe that you have these reusable modeling components, right? So you can write one self-contained model and then reuse it however often you like. So you can write something, this is silly, this is now some random slope submodel, and then you splice it into something else. So you have this random slope thing here. It returns some quantity, which is then dependent on model parameters or data that is passed to the model, and you can reuse it down here in some other model. Thanks. Yeah, and it basically does this by prefixing things, right? So actually, I'm guessing we're not seeing it, but basically, so in the generated Stan code, then the beta that shows up in the first model, it will then simply be called eta_beta, right? And then you can just continue from there. And then it's basically just inlining all of these things. Right, so what you can also do, which I think makes then also, which again, maximizes code reuse, is you can switch out components post hoc, right? So let's say you have written this first model on the left-hand side and you just want to switch out one prior or one modeling component, right? You can just then say, I want to take the space model and I want to add something else, or I want to switch something else out. In this case, in this example, for example, this white prior model here, it will be the same one as the random slope model here, just with the prior on beta exchanged by something else here, right? And then you can, of course, imagine that you don't have to swap out simple univariate priors, but you can also swap out like whole submodels, right? You can swap out anything that you want. You can change whether things are supposed to be data. You can change whether things are supposed to be parameters or are using submodels, right? So I think it's quite powerful. It's also a bit confusing, to be honest, right? So it's confusing all the agents that I try to let loose on this, on StanBlocks, both in developing and using it, right? And it's also sometimes confusing to myself. So I don't know whether this is not, as Claude would say, a loaded foot gun, right? So it's, I think it's a good idea. I don't know whether that really is that helpful, at least in the current system, basically. All right, so as I said, so the payoff is really not if you want to write this small self-contained model, but if you want to have reusable modeling components. I'm guessing Sean's sum-to-zero processing would be a good candidate for this, right? So all the downstream post-processing would be encapsulated in a single model that you just splice in, and you don't have to do anything afterwards. So how does it work? So people at StanCon will know that there has been something similar before, right? SlickStan by Maria Gorinova and colleagues. And as far as I know, SlickStan actually stands for slightly less intensely constrained Stan, right? So, and it was slightly lessly constrained, so they still had to, you still had to provide data. You had to say that some statements were data or not, right? But it was, it had a very similar idea. I think they, in some ways, went further, and in other ways, didn't go as far. Right? So their activity analysis tracing, for example, was much more powerful than the thing that I do. I didn't want to deal with all the things that they dealt with. That's why I restricted the top-level model structure. I think they went actually through all the indices and the for loops and everything, so did something much more involved than what I'm doing. But of course, then in the authoring, on the authoring side, I'm going much further. Right? So because I am porting features from the Julia language into Stan, which I mean they didn't need, they didn't want, they didn't consider, right? So there's some things where they went further, things where I went further, but SlickStan most certainly is the inspiration behind this. Yeah, in the end, both will give you Stan, right, so that you can inspect. I think actually, I don't know whether SlickStan actually in the end emits Stan. Right, so again, the example from the beginning, right? So here now you can see that there is this slightly optional type annotation for the alpha parameter, where you're saying this is now a vector of size j. This is again, like this is as close to Stan syntax as you can get in Julia, and this is absolutely not what you would ever write in Julia. Like this is not a valid type in Julia. So this is, again, so it's kind of in the middle between Julia and Stan syntax, confusing everybody, I think. Everybody but me who has developed this. So again, not sure how helpful this is. But yeah, in the end, so one of the key benefits of this is I think that you can only need to have a single model implementation, and then you can do all of your standard Bayesian workflow steps with that. Right? So you don't have to copy things around, you don't have to duplicate things in the parameters block, in the and generate quantities block, you don't have to switch out the whole model structure if you want to do population prediction or some cross-validation stuff, right? And the way this works now, for example, here, I mean, the one thing is very simple, right? So basically, in this model, if you don't pass y, so if you don't pass data, then the activity tracing knows that nothing of this depends on a parameter, basically, right? So everything can just move into generated quantities. On the other hand, if you pass y, if you condition on y, then you know that because y shows up here on the left-hand side of a sampling statement, and because you have passed it as data, that it's affecting the likelihood, and anything that affects y on the other itself, again, affects the likelihood and has to be a parameter of the model, right? And everything downstream then becomes generated quantity. And then there's like this other mode, which is a little bit weird. I implemented this 2 years ago. I thought it was clever. I think it's also confusing. But this basically allows you to rewrite your model in a way that allows you to do population prediction very easily. Right? So here you would basically be saying, I want to now predict for new subjects, and the subject thing now influences your random effects here encoded in alpha. And this would then tell StanBlocks to move everything affected by alpha into generated quantities, right? And then you basically still condition, you have your samples gotten from your fit of this posterior fit basically here in the middle. And then you subset your draws using bridge10 or whatever, right? And then you feed it into the new model, and you do everything that comes downstream of this y automatically, right? So because, I mean, here obviously y is the endpoint of the model, right? So there's nothing else coming downstream, but if there's anything else happening, which can be substantial, right? So this all gets handled automatically. Okay, so I'll skip this. So there's some, on the slides, there's some side-by-side thing, but you can look at it if you want. So because I don't have much time, so I started this before agents were prevalent. By now, I don't know how relevant this still is, because agents are good at writing Stan code, I think. They're very bad at using this tool, and they're very bad at using other tools built on top of this, just because there's no training data, basically, of this, right? Yeah, I mean, agents are good at producing, finding, and fixing bugs, both in my uses of this package, but also in the development of it, right? I still think it's valuable, right? So because it allows you to focus on the important things and don't have to actually parse the agent-generated Stan code. That's on what comes next. So basically, the next thing to work on is that my next dream is really that I don't even want to write Stan blocks anymore. Right? So I basically only want to interact with my PPL through some BRMS-like DSL, right? And this is so if StanBlocks is kind of a raw software package, this Bayesian regression model, it's still kicking basically. Right? So it's not even registered. I wouldn't recommend anybody to use this, but it's feasible, right? And it's relatively easy because StanBlocks is a much more amenable target for transpilation than Stan, right? Because StanBlocks already takes care of a lot of the things that you have to do to then in the end get the Stan code. Right. I'm not the only person working on this. I'm the only author of StanBlocks. There are other people from the Julia ecosystem which had similar ideas, right? So which are working on similar packages. It's among other things, Penny from Turing.jl. Simon is somewhere here in the audience, unless he abandoned me. Where are you? There he is. Okay. And there's also Sam Abbott, right? So and he actually developed a bunch of Stan-backed packages, right? So I think he hacked BRMS a little bit to produce epi-nowcast and epi-forecasts, right? And I think he actually now also has switched to Julia. And not because of StanBlocks, he didn't know about this, but I think because Julia in general, like it just allows you to do things more expressively. And yeah, so we are, I think, united in this want for a Julia-based BRMS kind of package. I think the potential is pretty big because I think it makes it easier to generate BRMS-like code and even add more features, right? I don't think it's there yet. Yeah, that's the end. That's again a link to the slides, and thank you very much.
All right, thanks, Nikolas. So again, we have time for one short question, and then we need to move on to the next session. So we have in the middle.
Yeah, Paul.
Thanks. I think you can talk more positively about your own achievements there. I was wondering, kind of the BRMS implementation in Julia, right? The one thing that makes R so good at this is because there's so much already there, like splines, etc. We have packages for this. So I was wondering, since I don't work with Julia that much myself, do we have all of these kind of things ready in Julia that we can quickly move from R to Julia for these kind of advanced regression models?
So splines in particular, I think, are a bit difficult, right? Because I think BRMS is using MGRCV or something, which does a lot of complicated stuff, I think, right? Which there is no equivalent of in Julia, as far as I know. So that is probably not as easy as I would wish, right? Other things are probably easier. I'm not entirely sure, right? So about the specifics.
Cool. Thanks.
And in principle, Julia, of course, it makes this promise, right, of composability. In principle, any package that you have in Julia would be able to interact with some, like actually running in Julia backend of this Bayesian regression models.jl, right? But I think currently it's not really there yet. In part also because the audience that is using BRMS, right? So they're not in Julia, they're using BRMS or R, right? So they're developing the packages there.
Yeah, makes sense. Thanks.
Okay, let's thank the speaker, and let's thank all of our speakers. Yeah.
Okay, so it's time for the flash talks. So we need like 2 minutes to set up. So if you want to stretch your legs,